how you can improve it better, and what are the good things you have written over there in your assignment. Okay, any more comments?
Sir, can you explain this blue line again?
Sorry, can you speak a little bit louder, please? Arya?
Yes, sir. Can you explain that blue line in the graph?
The blue line one more time. Okay, so the blue line is actually, so you can imagine the blue line and the black line in the sense that the blue line is actually have all the things in the same solution, but the protein coiling is not happening as strong as the black line. Okay, so in one of the form, they're actually forming this alpha helices. So let me explain that over here. Okay, can you see my screen?
No, sir. It's black.
Now it?
Now it's visible.
Yes. Okay. So what is there? Let me write down this. This is the quiz 2 discussion. So the most important thing was that in one part, what is actually happening that you have this alpha helix system, and which is connect. Oops. So one, you have this alpha helical system, and which is connected through the nucleotide. Okay, this is a nucleotide, and this is the alpha helix. And then you put 3 of them. And in there are different nucleotides, nucleotide 1, nucleotide 2, nucleotide 3. In one of them, they are actually remaining apart. They are not forming interaction between themselves. So how their CD spectra will look like? Very similar to their individual alpha helices. Okay, there's a little bit of increase because there's probably a little bit of interaction going on. But what happens if they actually form a very good interaction, especially at the bottom? I should have done in the different colors. So over here, the nucleotides are forming a very good interaction at the bottom. So that brings all the alpha helices close enough. And due to that, what happens, all the alpha helices are now close enough to form a very good interaction between themselves. Okay. And how to look into it, actually it looks very easily from the top of that actually. So what happens, alpha helices 1 actually like this, alpha helices 2 is actually like this, and alpha helices 3 is actually like this. So now you can imagine, I'm looking from the top version. Okay, so previously what was happening, all the alpha helices was alpha helix on their own position like this. If I'm looking from the top, all the helices looks like this. But once they're forming an interaction between themselves, they actually like a little bit do a shearing force and actually wrapping up around each other. And that is actually creating a alpha helicity in a supramolecular level, not only in their individual level, but in a supramolecular level, they're interacting. And that is actually showing up in a much more increased propensity of the alpha helical response of the CD spectrum. Does it answer your question?
Sure. Yes, sir. Actually, what I was thinking at that time is in the reaction there is in the control sample there is no reaction between this nucleic acid and this peptide thing, and they are totally separated. And since they are not interacting here, we can find out
yes,
internuclear.
Yeah, I mean, you're ending up with the right conclusion. A little bit of here details like exactly what is the interaction between nucleotide, all those things. That is not the main part of this question. The main part of the question: do you understand that if there is a formation of a super helicity among the alpha helices, I can follow that via CD spectroscopy. So CD spectroscopy is that much sensitive for that. Okay, so that is the question.
So okay, we have taken the 3 oligonucleotides, right? So if we increase the number, then also the alpha helicity will be increased.
Yes, you can do that. But generally what happens is this particular system is actually known as 3-helix coil. Okay, that means 3 helices forming a coil itself. So you can form 4-helix coil, you can form 5-helix coil. So it is found that the 3-helix coil is actually the most stable or more easiest to stitch together. 4 helical bundles are also known, but 3 helical bundles are the most commonly found. Okay. So that is because of their spherical hindrance, because you are putting so big helical structures close together and you are creating a shear strain. So it is found that when you put 3 of them, it is actually managing, and as I saying all the time, that it is thermodynamically favorable, that you are creating a strain. So it is actually thermodynamically unfavorable, but you are still creating some interaction between the helices. So that is actually compensating that. So it is actually compensated when you have 3 helices. 4 helices, sometimes it occurs, but beyond that, it doesn't occur. And 2 helices, it is 2 minimum interaction, so it doesn't occur very well. So 3 is kind of the magic number to create this kind of helical coil. And it is the most commonly found in biology, even in synthetic chemistry. Okay. Okay. Any more queries? Okay. If not, so this is the part of where we discuss about the CD spectroscopy. So the main take-home message for the CD spectroscopy, if I want to point it out by one. So first thing, we learn that what is chirality, okay? And then how I can measure chirality. I can do that by optical rotation, or what is known as circular birefringence. Or I can also do that by circular dichroism, which is actually also known as mole ellipticity. Okay. And now you know why it is called ellipticity and all those things. That is because the left hand and right hand circularly polarized light are different for this one, or the refractive indices are different for this one. That is what I am showing. Then we discuss about the molecular origin. What is there in the molecule that it actually interacts with the right hand and left hand circular polarized are different, and you can say that what is the molecular origin of the CD. Then we go to the examples of it. We look into the protein structures, how it is different. We have gone through the DNA structures, how it is different, and their other differences and other explanations. Like I can follow their structural dynamics, I can follow their denaturation, I can follow their stability, all these things by CD spectroscopy. And if you remember, Professor Chidambar Kulkarni actually discussed about polymers, and now you probably can appreciate it better, because protein structures or DNA structure, nothing but polymers of amino acids or nucleotides. So you can design another polymer which actually creates a helical structure in the 3-dimension or in a supramolecular structure, although the monomer may not be chiral. So those kind of structure can also be CD active. And sometimes your monomer can be chiral, but depending on their interaction, how they're doing, your chiral environment may be different for all the different kind of secondary structure, very similar to the alpha helix or beta sheet structure in protein. And over there, you can also see the difference. And I have uploaded a paper for reading, and thanks to Rijwan, who actually pointed that towards my notice. So I have, it's a very nice paper. So I have also uploaded that in your supplementary reading. Okay. And as I'm saying again and again, it is a PhD course. It is not, this is not kind of a course where I actually mostly judge that how good of a student you are. Over here, we try to give you newer thought processes and try to engage you into learn new things. So over there, main goal is to teach you how to read papers, teach you how to think about something that you probably don't know or didn't face earlier. Okay. And over there, my main goal is to find out how good each of you can be in your own way. I am not going to spend too much time try to pit each of you against each other, like if student A is good or student B is good. Over here, I'm trying to get if each of you can reach the best of you so that it can help you in your future PhD life. And over there again, CD spectroscopy is just an example. Over there, I'm trying to show you if any particular spectroscopy, how you should look into it. You look into it like what is the molecular reason for that, why it is happening. You have to understand that. You have to understand the basic physics of that, how it is connected to chemistry, how it is connected to applications, and application mostly go to material science or biology. So all of them are actually connected. So break down your shackles that I am an organic chemist or inorganic chemist. I won't go beyond that, because science is science. We actually differentiate them according to our need as inorganic or organic chemistry or physical chemistry. But if you want to understand something, it is just science. So break down all these invisible shackles and try to follow and try to understand it. Don't think about it, oh, it is physics, I don't need to understand. Go ahead with that and try to find out what is the answer for that. And follow that until and unless you yourself are not convinced that you understand it properly. And what is one of the best way to understand it properly? There are two ways. Either you can teach. For an example, when I am teaching, when I begin the class, I probably don't understand the things pretty well. But when I'm teaching you guys, I'm actually understanding it again a little bit better. Similarly, you also need to try to teach someone. The first example is probably yourself. So just take a piece of paper and try to understand from the beginning on a blank sheet of paper, try to put all the thought processes, why it is happening, and try to find if you can explain that with very simple physical phenomena. If it is not, then you probably is not there at the end of understanding. If you're just saying that because of this, some reason it is probably happening, that means you're not understanding. If you can explain, oh, because of this simple reason this is happening, this is connected to this is connected to this, and you have a very nice logical chain of thought process, you are understanding it properly. And I'm quite sure all of them can reach that space, because if I can reach, all of you can reach. Okay, so this is the thought process of thinking, and this is one of the examples where we actually talk about CD spectroscopy. So the next thing we are going to talk about Mossberg spectroscopy. So Mossberg spectroscopy, before we begin, any more comments or any suggestions from anyone? Okay, if not, we'll go further about Mossberg spectroscopy. So again, very similar to CD spectroscopy, we try to first find out what is Mossberg spectroscopy, what is the basic physical phenomena behind it. So we'll learn some very basic physics, and don't worry too much because I don't understand physics pretty well. So I will leave it very much school level physics. And then we'll look into a lot of examples of different chemicals where we can use Mossberg spectroscopy to find out the information about the structure of a molecule. Okay, and as I again saying probably twice or thrice now in the class, why spectroscopy is very much important. You have to understand, when we are actually making a molecule or designing a molecule, we are actually designing and or creating it or originating it in the molecular level. Its structure is mostly in the nanomole, in the nanometer to angstrom level. But we exist in the centimeter, millimeter, or even meter level. So there's a huge difference in order of magnitude. It is 10 to the power 8, 10 to the power 9 orders of magnitude difference, what we are creating and what we can actually visibly see. So we need something that we can get a signal or get a trigger even in the molecular level, which will be translated even in the macromolecular level. For an example, a transition metal absorbing a DD transition in the visible region, and you're seeing a very nice colored solution. The colored solution, a blue or a red solution, I'm seeing in my naked eye, that means in the macromolecular level. But why it is happening? Because of the DD transition. A light is hitting on the D electrons and it is reorienting itself, and this is happening in the angstrom level. So that means through spectroscopy, we can bridge the gap between the microscopic or even nanoscopic level to the macroscopic level. So that's why all the spectroscopy are very much important. And if you look into all the spectra